Hello, and welcome to this lecture on probabilistic models. I am Jaakko Peltoniemi, Professor of Statistics and Data Analysis at University of Tampere. So, let's talk about people. People are all different from each other in various ways. They each have properties that make them individuals, but they also tell us about what people are like. We'd also talk about, for example, apples. Apples are each all different and separate, and they each have their properties that make them individual apples, but they also tell us about what apples in general are like. Or we could talk about books. Books each have their different contents and their unique messages, but they also tend to tell us about what kinds of things people write books about. So all of these things are examples of cases where we have a set of measurement data with many different data items. For example, n different data items and several different things that we could measure about each data item. For example, if we are talking about people, we could have a set of 1,000 people where we record, for example, 150 different types of information about each individual person. These could be things such as their age, their height, their weight, how much they earn, how many contacts they have on Facebook or Twitter, and so on. So these people can be considered a sample, a random sample of a larger population. And we may be interested in asking questions about this larger population, such as, are there some typical common properties among the people? Are there some typical ranges of variation in the features that we have measured? Are these features somehow related to each other over the population of people? Do these properties tell something about the larger population? And are our findings about the population reliable? To answer questions like these, we need probabilistic modeling. Probabilistic modeling is a tool that statisticians and data analysts use to explore statistical phenomena. Probabilistic modeling tells about these phenomena, which means that it doesn't only tell about an individual sample, which could be, for example, one person. It also doesn't only tell about a particular available data set, for example, a set of 1,000 people that we have gathered. It tells about the underlying phenomena behind these data. And it helps us to summarize these phenomena by the statistical properties of those phenomena. It also helps us to summarize individual data sets, such as sets of people, by using the properties of the underlying phenomenon as summaries. It helps us also to understand the individual samples in context of this phenomenon. For example, we can then say things like whether a person's height is unusually large compared to the phenomenon of what people's heights are like. It helps us to predict properties of new samples that we haven't encountered yet. And it also helps us predict missing properties in samples that we have gathered, where we have seen some properties, but we are missing some other properties. To understand statistical modeling, we should first discuss some basics of probabilities and random variables. So random variables are things that vary. They can get different values each time we observe them, and those values are coming from some underlying distribution. There are typically two types of variables that are considered. Discrete valued random variables, which have a discrete set of possible values. An answer to a multiple choice survey question is an example of this kind of variable. There are two special cases worth mentioning, which are binary valued random variables, which is, for example, a coin flip, which can get either heads or tails in each flip, or a true-false statement in a survey. Another special case is ordinal valued variables whose values have some order from small to large. For example, a die, which has 6 values in order of magnitude, or a university course grade. The other type of random variable is continuous valued random variables, which, like the name says, they take values from a continuous set, a range typically. For example, heights of people, weights of people, temperatures, those are all continuous valued variables, which can be random variables. Now, observations then are things that we record about these random variables when we gather samples about them. Now, we record values that we observe for the random variable. A recorded value of a die, heads or tails, a coin throw, 1 to 6, or a recorded value of a person's height or weight, or temperature outside in a particular day. These are all examples of samples of random variables. A probability tells us how likely a particular value of a random variable is for discrete valued random variables. That means how often it occurs in repeated measurements, or how strong our belief is in the value occurring. The difference between these interpretations is a matter of philosophical debate that we will not talk about during today. For continuous valued random variables, each set of outcomes would have a probability, but an individual outcome instead has a probability density. Now, for both types of random variables, a probability distribution will tell this probability or probability density for each possible value. So, for example, a coin could have 50% as the probability of heads and 50% as the probability of tails. Now, a probabilistic model is instead an attempt by us to estimate this behavior of a random variable. The model will then define a probability distribution for the variable, telling the probabilities or probability densities of each possible value, and usually those models have some adjustable parameters which are optimized to fit a set of samples that we have gathered about the random variable, meaning samples that we have gathered about some phenomenon that interests us, for example, some set of people, or a set of apples, or whatever is the phenomenon we are interested in analyzing. Now, if the model is well fitted or well estimated, then the model will approximate the behavior of this random variable, this phenomenon, well enough that the model can be used to both explain the variable and to predict its values. When we discuss statistical models, probabilistic models, statistics are an important part of that. Statistics are important numbers that tell about the behavior of a random variable. In different models, these statistics can be different things, but in each case, they represent some crucial aspects of the model. Estimating these crucial statistics from observed samples can either be used to define a model for the random variable, but it is also so that if we already have a model of the random variable, we can use this model to compute these statistics based on the model. Now, for univariate models, models where there is only one random varying number, a couple of important statistics are the mean, which is the expected value, the expectation of this random value over the distribution of the underlying variable. It is often denoted as mu, and in mathematical terms, it is the expectation over the probability distribution px of the values x of this random variable. Another statistic that people often talk about is variance. This means how far the values of this random variable tend to get from the mean, how far apart they can be from the mean. In particular, the variance is the expected squared difference of the random variable values from the mean. Variance is often marked as sigma squared, and mathematically it is the expectation over the distribution px of squared differences x minus mu. X minus mu is directly the difference of the observed value x from the mean mu, and we take the square of that, and we take the expectation of that over the distribution. Often we also talk about standard deviation, sigma, which is simply the square root of the variance. Now, in particular, it is useful to be aware that the standard deviation is really a square root of a variance. It is not the same as the expected distance of the random variable from the mean. It is similar but not the same. There are also many other common statistics that people talk about when they talk about random variables. This includes, for example, the median, the quantiles or the quartiles, the maximum and the minimum value. So we won't get into these other statistics, but it is useful to be aware of them as well. It is useful to be aware of a couple of important distributions for both discrete and continuous variables. For discrete variables, I would like to introduce the multinomial distribution, which quite simply states the probabilities for each individual possible value of this discrete variable. For example, if it is a variable that tells the favorite type of pet for a person, then this distribution would simply list the probabilities for each possible type of pet. For example, cats, dogs, rabbits, and so on. And the parameters would be the probabilities for each type of pet. For example, this picture has an example where cats have probability 0.2, dogs have 0.3, rabbits 0.1, fish have 0.15, and so on. So all of these values together must sum to 1. And that means that the last one of these probabilities must simply be 1 minus the rest. A special case of this multinomial distribution for binary variables where you only have 2 possible values is called the Bernoulli distribution. And there are also other discrete distributions that you may encounter, such as the binomial distribution, the negative binomial, the Poisson distribution, and a few others. For continuous variables, 2 distributions that are worth talking about here are the uniform distribution and the normal distribution. The uniform distribution means that the probability density of a variable x has probability 1 divided by b minus a if x is somewhere between the values a and b, and elsewhere the probability of x is 0. So the parameters of this distribution are simply what is the lowest possible value with a non-zero probability density, so that's a, and what is the highest possible value, that's b. So in the picture we have that a is 2.5, b is 5, and that means that between a and b the probability density of x is 0.4, and outside that range the probability of x is simply 0. The other continuous distribution that we would like to talk about is the normal distribution, also called the Gaussian and shaped like the well-known bell curve. Now, that distribution has a mathematical function which is that at a location x, the probability density is 1 divided by the square root of 2 times pi times the variance times the exponent of minus the squared difference between x and the mean mu divided by 2 times the variance. So the picture here shows an example where the mean of this distribution is set at 2.5 and the variance and also the standard deviation are set at 1. So the bell curve then has the shape in the picture where it is centered at 2.5, and the parameters and also the important statistics for this distribution are the mean and the variance. There are many other continuous value distributions that you may encounter. These include the gamma distribution, the inverse gamma, the t distribution, and the Laplace distribution, and many others. So far we've talked about distributions that involve only one number that varies, so-called univariate models. But there are also multivariate models which we want to talk about when we have phenomena that involve several types of measurements for each sample. For example, people can have heights and weights, stock prices can have values both today and tomorrow and next week, and traffic can have different values at different places around the city, and so on. So a multivariate model tells about these variables and their relationships. It can be used to predict the values of a variable based on known values of the other variables. So multivariate models can have multivariate statistics, which tell how much these variables are related. An important such statistic is the covariance, which tells how much two variables x and y vary up and down together. In mathematical terms, it is the expected value of how far they are from their mean together. So it is sometimes marked as sigma xy, which is the expectation over their joint distribution of x and y of the difference between x and its mean times the difference between y and its mean. Instead of the covariance, sometimes people also talk about the correlation coefficient, which is a kind of normalized version of covariance. It is quite simply this covariance value divided by the standard deviation of x and the standard deviation of y. So this correlation coefficient has a value which is always between +1 and -1. So this is easy to talk about because it always has the same possible range. And value 0 means the variables x and y are uncorrelated. Now, multivariate distributions also have several different forms. One that we would like to talk about is the multivariate normal distribution. When you have a vector, a random vector containing d different variables, x1 to xd, that vary together, then they together have a distribution where the density at a particular vector value x is 1 divided by 2 times pi to the power of d divided by 2, where d is the number of variables, times the square root of the determinant of sigma. Sigma here is the covariance matrix of this random vector. And this thing is then multiplied by an exponent term, where inside the exponent you have minus the product of x minus mu, which is a vector, transpose, so that it is a row vector, times the inverse of the covariance matrix, times this x minus mu vector again without the transpose, divided by 2. Now this multivariate normal distribution has several parameters. It has a mean vector, denoted also mu typically, just like a univariate mean is, maybe with a bold symbol. And it has this covariance matrix sigma. Now inside this covariance matrix there are several values. The diagonal values in this matrix contain the variance of each individual variable x1 to xd, and the off-diagonal values tell the covariance of each variable pair. This example picture here shows a multivariate normal distribution with two variables, so its mean is located at 2.5 for the first variable and 3 for the second variable, and the covariance matrix has value 2 along both diagonals and value 1 along the off diagonals. There are also some other multivariate distributions, such as the Dirichlet distribution, the Wishart distribution, and the multivariate versions of the t-distribution and the Laplace distribution. In order to get good probabilistic models to analyze, those models must be fitted to a set of available data. This is a crucial step. It needs to be done before we can make any predictions about the underlying phenomenon, and there are several ways in which it can be done. Now, first of all, sometimes people talk about estimating individual statistics. This is not the same thing as fitting an entire probabilistic model, but this is still something that people have a practical interest in because those statistics can themselves already be informative. So that's why people create estimators, functions that can estimate statistics based on a set of data. The results of those functions are called estimates. So an estimate of the mean can be obtained by taking a sample average of a set of n samples. So if mu is the symbol for the mean, then mu hat is a symbol for the estimate of the mean. And it is quite simply 1 over the number of samples times the sum of the sample values over the n samples. A similar estimate of the variance can be taken by taking a sample average of the squared distance from individual samples to the mean. So if sigma squared is the symbol for the variance, then sigma squared hat is the estimate, and it is the expectation of the squared distance between sample values and the mean. The estimate can be computed by, again, taking a sum over samples, I goes from 1 to n, for each sample taking the squared difference between the sample value xi and the estimated mean from the previous equation, taking this squared difference, summing that over the samples, and then dividing by the number of samples. Now, these estimators, these functions that give you these estimates, they are themselves random variables, because the estimate is computed from a set of samples, and there is randomness in what samples it gets computed from. Now, this estimator can therefore be a biased random variable if this expectation of this estimator differs from the true value of the statistic that we are interested in estimating. In that case, the bias of an estimator, for example, sigma squared hat, is stated to be the expected value of the estimator over the choice of the data minus the true value of the statistic that we are trying to estimate. If the bias is 0, the estimator is unbiased. If it is non-zero, then it is biased. Instead of only estimating statistics, full probabilistic models can be fitted to data in several ways. One such way is called maximum likelihood fitting, which simply means that we want to find the model, the choice of parameters that best explains the available data. That means we want to find the particular parameter values, for example the mean and the variance for a normal distribution, that make the set of data that we have gathered look as likely as possible, that finds the highest value for their probability. So if we mark the parameters together as theta, then the maximum likelihood estimate is the choice of theta that maximizes the probability of data given the parameter values theta. If we have a set of individual independent samples, then this maximization is the same as maximizing the product of the individual probabilities of samples xi given theta. Another possibility is to find the maximum a posteriori estimate of parameters. This means we want to find the model that is the best compromise between explaining the available data and being, in a sense, reasonable according to our prior knowledge, meaning what we think is a good choice of parameters before we have seen any data. The maximum a posteriori or MAP choice of parameters is the one that maximizes the product of the probability of the data given the parameters theta times the prior probability of theta. Priors can take many forms, and the choice of the prior is something that is, well, something that is the subject of a lot of philosophical discussion. It is also possible to instead of fitting a single choice of parameters, to compute instead the whole posterior distribution of parameters and their probabilities given the data. So this posterior distribution is a distribution of parameters given the data and the prior that we have for the parameters. It is computed according to the Bayes rule, which says that the posterior probability for a parameter value given data and the prior is the same as the probability of data given that parameter times the prior probability given that parameter divided by an overall probability of the data. When we just want to sample from the posterior, often it is enough that we are able to compute these two terms in the numerator, the probability of the data given the parameter and the prior probability of the parameter, and then we can use various choices to sample from this posterior. Sometimes we can do things in an even better way. If the likelihood function and the prior in a way work well together, so that they are mathematically called conjugate distributions of each other, it turns out that this posterior distribution can be computed analytically so that it becomes a simple distribution whose statistics can be easily computed. But otherwise, we instead try to approximate the posterior distribution either by sampling a set of values, a set of sample parameter values that are distributed according to this posterior by methods such as Metropolis-Hastings sampling or Gibbs sampling, or by computing a variational approximation, a simple mathematical distribution that is fitted to this posterior so that it tries to contain one of the peaks of the actual posterior. How to compute these approximations is beyond our discussion today. One of the most important things we often want to do with probabilistic models is to predict some of the variables from other variables. In multivariate distributions, this is done by using conditional probabilities. The chain rule of probabilities says that if we have several variables that we observe together, let's say x1 to xt, and there is some additional variable xt plus 1 that we would like to say something about, we would like to predict, then the joint probability or the joint probability density of the observed variables and this missing variable together can be expressed as the product of two things: the conditional probability of the missing variable given all the observed variables times the probability of the observed variables. In other words, the conditional probability there can be written as the ratio of the joint probability of all the variables together divided by the probability of the observed variables. Now, one of the interesting things about this rule is that sometimes when the joint distribution, the multivariate distribution of all the variables x1 to xt and xt plus 1 together has a simple enough mathematical form, then sometimes this conditional distribution of xt plus 1 given all the observed variables can be computed easily. In particular, when the joint distribution of all the variables together is a multivariate normal distribution, then it turns out that the conditional distribution of one of these variables or some of these variables can be computed in an analytical form. It actually turns out that this conditional distribution of some of the variables is itself a normal distribution. So let's say that we would have variables x divided into two groups, x1 and x2, and we would like to compute the conditional distribution of x2 given some variables x1 that we have already observed. So it then turns out that the probability density of x2 given x1 is simply a multivariate normal distribution, which means that it has the same form as the multivariate normal distribution that we encountered before on the previous slides. That means that its probability density is simply 1 divided by 2 times pi to the power of d2 divided by 2, where d2 is the dimensionality of x2, times the square root of the determinant of a covariance matrix. We'll come to that covariance matrix soon, but there is a covariance matrix whose determinant we are taking here. Now, this constant term is multiplied by an exponent, where inside the exponent we have minus x2 minus a mean, and we'll come to a mean too very soon. So x2 minus a mean transpose times the inverse of that same covariance matrix that we mentioned before, times again x2 minus the mean, and all of that divided by 2. So this is a multivariate normal distribution. So there is no mathematical difference in the general form between this and any other multivariate normal distribution. The interesting thing is, how do we compute the value of the mean and the value of the covariance matrix that is needed here? And it turns out that the equations for these are relatively simple. The mean of this conditional multivariate normal, let's denote that by mu c, has the value mu2, which is the original mean of the x2 part of the multivariate joint distribution of x1 and x2 together. So that's the mean of the x2 part in that joint distribution. But then we add to it another term, which is sigma 2,1, which is a cross-covariance matrix between x2 and x1. In other words, that's an off-diagonal part of the total covariance matrix of x2 and x1 together. That matrix is multiplied by the inverse of sigma 1. Now, sigma 1 is the covariance matrix part for x1 alone. And then that in turn is multiplied by x1, the observed values for x1, minus mu1, which is the original mean of x1 in the joint distribution. So by computing this equation, we will get a value for the conditional mean of x2 given x1. Similarly, we can get the value for the covariance matrix of x2 given what we have observed about x1. It will be a similar equation here. So the conditional covariance matrix, let's call that sigma c, will be sigma 2, the covariance part of x2 in the joint distribution, minus sigma 2,1, the cross-covariance matrix, times the inverse of sigma 1, times the transpose of that same cross-covariance matrix. So what this practically means is that the mean, the conditional mean, can go up or down depending on what kinds of values of x1 we have observed. The covariance matrix of sigma 2 will basically be decreased because we have learned something about that variable by observing x1. So the picture here at lower right shows an example where the two dimensions x1 and x2 have the same distribution as in the previous example about the multivariate normal distribution. So the mean of the joint distribution is 2.5 for x1 and 3 for x2, and the covariance matrix of x1 and x2 together has 2's in the diagonal and 1's in the off diagonal. Now if you insert those values into the definitions that we talked about, then using that you can calculate the conditional distribution for any observed value of x1. For example, if we observe that x1 has the value 4, then we can ask that, okay, given that observation, what is then the distribution of x2? And it turns out that if you insert those values into the equations here on this slide, then you will get that the mean, the conditional mean of x2 will be 3.75, and the conditional variance of x2 will be 1.5. Now notice that the conditional mean is higher than the original mean of x2 was. This is because the knowledge of x1 has increased the mean of x2. Basically, we know that we are in a part of the joint distribution where x2 tends to get higher values. Notice also that the variance of x2 has decreased. From the original variance 2, we now have variance 1.5, which means that by learning the value of x1, we have gained more information about x2, and therefore we have less uncertainty about x2 anymore. So the parameters of this computation of conditional distributions are mu1, which is the original mean vector of x1 in the joint distribution, mu2, the corresponding mean vector for x2, sigma 1, the covariance matrix of x1 in the joint distribution, sigma 2, the covariance matrix of x2 in that same joint distribution, and sigma 2, 1, the cross covariance matrix between x2 and x1 in that same joint distribution. All of these are things that we can estimate from data samples using the kinds of estimators that we saw on the previous slides for means and for variances. So what we have just learned is that if we can provide this joint distribution of multivariate random variables, x1 and x2, as a multivariate normal distribution, if we can describe what the means of the variables are, if we can describe what the covariance matrices of those variables are, then we can always calculate the conditional distribution of one variable given the other variables very easily. Now this same idea can be used to learn flexible input-output regression functions in an approach that is called Gaussian process or GP regression. In Gaussian processes, the idea is that suppose that we have some input locations where we would like to predict some output value. We'll have some examples about that soon. There can be very many such locations. There can be even infinitely many potential locations. So we might not want to specify every one of them separately. But the idea is that the output value at every one of those input locations will be a random variable, and we will assume that they all are together distributed as a multivariate normal distribution. The idea is that we have observed some of them as a data set of values x1 that have been observed at some particular set of the input locations, a subset of them. And now what we want to do is we want to predict the distribution of the rest of the output values, the values at the rest of the input locations. So in order to do this, For each one of these new variables, the new locations where we want to predict, all we need to do is to somehow provide the original mean and variance and cross-covariance values to this joint distribution. Because there can be so many locations, we don't want to manually write out every one of them. Instead, we want to somehow specify these values as a function. If we can do this, if we can specify these functions, then we can compute the conditional distribution at the locations x2 using the same equations that we just saw for the multivariate normal distribution. In this way, the Gaussian process actually provides a prior over input-output functions, or possible functions that could relate the input locations to the output values. And then the conditional computation that we just saw for the multivariate Gaussian, that will provide the corresponding posterior after seeing some of the output values at some of the input locations. Because this allows every input location to have its own distribution of output values, this kind of regression is very flexible. It can represent many kinds of highly nonlinear input-output functions. In order to use Gaussian process regression, all you need to do is to suggest a function, a mean function, that would tell the prior mean for the joint distribution of the variables. Now, of course, in order to make this suggestion, you would probably need to have some information. So what you can use for that is the input locations. So these input locations may tell something about the roles of these variables. And we are free to use that information. We just don't know the output values yet. So we cannot use anything about the output values right now. So we are going to use this information about the roles of these variables, their meanings, to fill in the means mu1 and mu2 of the joint distribution. Similarly, we need to suggest some covariance function that would tell the prior covariance in the joint distribution between any pair of the variables inside the x1 multivariate variable, or inside the x2 multivariate variable, or between variables inside x1 and x2. And here also we can make use of the input information about the roles of the variables. We just can't use any knowledge of the output values yet. So we are going to use this information about the roles of the variables to fill in the covariance matrices sigma 1, sigma 2, and the cross-covariance matrix sigma 2, 1. Once we have used these two functions, the mean function and the covariance function, to fill in the means and the covariance matrices, then all we need to do is use the same equations that we just saw to calculate the conditional mean and conditional covariance for the variables x2 given our observations of x1. So let's have some examples of this. Suppose that we want to predict, for example, stock prices. The above picture here is a picture of the New York Stock Exchange, but we are instead going to predict stock prices closer to home. So we're going to predict stock prices in Helsinki. Specifically, we are going to predict stock prices related to the Helsinki OMX 25. And in order to do this, as we just said, we need to provide for each variable that we want to predict the mean, the variance, and the cross-covariance values as a function. So in this case, the variables x1 that we have observed would be stock prices, for example, from some day 1 to day 10. So some previous days where we have already observed stock prices. And x2 would be stock prices in days that we have not observed. Typically these would be future days, let's say day 11 to day 20, and we want to predict the distribution of these future stock prices given the previous stock prices. So now we would just suggest some prior mean for the stock prices based on our knowledge about the roles of these variables, meaning that we know that they are stock prices. For example, we could suggest that the mean would be 100 euros at all times. When we haven't yet observed anything, that might be a good enough guess. Why not? And we would use these to fill in the mu1 and mu2. Then we would also need to suggest the prior covariance matrix for the set of variables that we want to predict over. Meaning we would like to suggest a function that we can use to fill these matrices. So, for example, we might say that stock prices at close-by days would likely have a stronger covariance than stock prices at far-apart days. So we might say something such as the covariance between stock price in one day and at another day k days apart from it would have a covariance proportional to, let's say, the exponent of minus k squared. This is not the only possible choice, but it could be one possible choice. And we would then just compute that function for every pair of the days that we are considering and use this function to fill in the sigma 1, sigma 2, and sigma 2, 1 matrices. So let's really do this for the OMX Helsinki 25 index. Let's take the daily index values from late October 2017 to, well, October 19 of 2018. And our task is to predict this index value at future dates. Now, as the mean, we will just set a constant. Instead of just setting it to some, let's say, 100 euros, we will actually take just the average of the observed stock prices over the year, over the previous year. And for the covariance function, yeah, let's just say that for time points that are d days apart, we will say that the covariance will be something of the form c times the exponent of minus d squared divided by b, where c and b are some constants. And then additionally, if we want to talk about the variance at a particular observation, then we should also add some observation variance to distinguish what we want to say about the underlying phenomenon from the variance that can happen in individual observations. So we'll add some additional variance for the special case that d equals 0. So we will set this c constant to the variance of the index value over the past year. We will set b to just 100, for example, and the observation variance we will set that to 200. If we do that, then the picture below is the result. In this picture, the green dots are the actual observed index values for every day for the past year. The black line is our conditional mean. It is our predicted value at every time point, including the past days and including future days for the next half a year, roughly. And the red curves above and below the black curve, they are the curve of the mean plus one standard deviation, which we can calculate from the covariance matrix that we get for x2. So here what we can see is that first of all we have learned the function that seems to match well the actual observed data. The black curve and the red curve seem to roughly contain the variance of the stocks, not the most extreme changes, but roughly it seems to follow the progress of the stocks. And what we can see here is that it also provides a prediction for future days that we have not seen yet. In this case, it is saying that the stock prices would go down a little bit further and then they would rise back towards the yearly mean. And you can see that the red and black curves go further apart from each other as time goes on. This is because we know less and less about those future days. We have less and less correlating information with high covariance with the future days as we go further and further from what we have observed, and therefore the covariance matrices that we get in the prediction, they will have larger and larger values, meaning that the red curves will go further and further apart from the predicted mean curve. Let's take another example and predict temperatures in Tampere. So now our input locations are days at different parts of the year, and our outputs are air temperatures measured at Tampella in Tampere. So we would like to predict temperature at all different times, including future times. So again, we use these roles of the variables, the fact that they are temperatures at different days, as a guide to creating a mean function and a covariance function. The mean function in this case will be just a constant, the average temperature over several years. Our covariance function will be to say that, okay, if we have some measurement locations d days apart, then we will again say that the covariance would be c times exponent of minus b squared divided by b, and then some observation variance in the case that b was 0. Here we will set c to be the variance of the temperature over several years, and b we'll set that to be 10,000, and the observation variance will set that to 10. So we have gathered temperature data from several years back, and when we take these as the observed locations, as the x1, now we can predict x2 as the temperatures at all locations, including future times. And the result is the picture below, where the green points are the measured temperatures, black is the mean conditional curve that we predict, and red is again the same as the mean plus one standard deviation. So we can see that the curve follows the temperatures pretty nicely over the past years, and we can see that it over the future time seems to predict something for the first upcoming future days, and then it goes towards the overall average, kind of as expected, because for very far future times we don't really know a lot. Let's take a third example, which is sort of a counter example. So here we are trying to predict something geographical, locations where there are mountains, and we would like to predict heights of the land at all places around the mountains. So we are going to take Mount Everest and the area around that as our area of interest, and we will have as our data the locations of all the mountain peaks in a 500-kilometer radius around Mount Everest, plus also some towns and cities and villages with known elevations. This comes from OpenStreetMap, and we want to predict the height of the land in all of the areas. So again, we will set a mean function to be constant, the mean height of these recorded elevations that we have gathered. And the covariance function will again be similar. If there are some land locations which are some distance d apart, now this is a geographical two-dimensional distance based on latitude and longitude coordinates, so we'll set the covariance function to be again c times exponent of minus b squared divided by b plus some observation variance for b equals 0. Here we set c to 0.1, b to 0.01, and the observation variance to 0.1. Now this is a two-dimensional example, but otherwise everything else happens just as before. We use the same equations to compute the conditional distribution, and we get a result that looks like this. So, unfortunately, the picture here is something like a failure, really. Now, mathematically, it looks fine. The curve, again, in the places where the mountain peaks occur, seems to match the observed heights of the mountains. And it does vary smoothly between them. But we see that it suggests some very high peaks and some very low valleys in places where we don't have observations. So this is because this function assumes that our samples have a good coverage of the area we're going to predict, and it also assumes that our samples are representative of the underlying distribution, whereas here they are actually mostly mountain peaks representing extreme values of the distribution rather than just values all throughout the distribution. So because of these differences, this kind of Gaussian process approach is not really the best approach for this geographic case. Now, another thing that we can say is that in all of these previous examples, we just specified the mean and the covariance functions and set some particular values for the parameters. It's also possible to optimize those parameters by fitting them to observed data. The reason why this is possible is because the observed part, the x1s, observed stock prices, temperatures, peak locations, according to our assumption, they also follow a multivariate normal distribution. So based on the covariance function and the mean function, we can calculate the probability of these observed data, meaning we can try to compute parameters of those mean and covariance functions that would make the data look as probable as possible. This would give us a maximum likelihood solution for those parameters, and we can similarly also consider a prior for the parameters and find a maximum a posteriori choice. The equations are basically the same as what we saw on previous slides. We maximize the probability of the observed data, which is a Gaussian probability, or we maximize that times the prior probability of the parameters. That optimization can be a little bit more complicated because it depends on the form of the mean and the covariance functions, which can be of many different forms. But there is software available for many programming languages that can perform this maximization for a range of popular mean and covariance functions. Lastly, if you want to find additional resources, for the basics that we talked about, look at any statistics textbook. For the Gaussian processes, look at the Gaussian process website, which includes also software for several programming languages, or you can look at the reference papers mentioned here. I also want to mention our international master's program in computational big data analytics at Tampere University. The slogan of that is Make Sense of Big Data, and it offers teaching in many things related to data analysis, statistics, probabilistic modeling, but also many computational aspects and other related topics. My own research group performs research on topics related to these kinds of models, on data including social media and much more. And we have occasionally, I would say even regularly, student positions available, so feel free to ask us. Thank you for taking part in this lecture. I hope you enjoyed it.